Okay, we are starting chapter 4. It is the last chapter that is focused on derivatives. Then we get to integrate. So in this chapter, you're expected to be confident with your taking derivatives. And you want to leave this chapter feeling more than just confident. You want to leave feeling like a pro. Because when integrals show up, you're going to have to take all your derivative formulas and go backward on them. If you don't know them well, do you realize how bad things are going to be for you when you go backward on them as well as forward? And it even happens by accident, no matter how well you know your formulas. So make sure that you understand you've got to practice these rules with like flashcards, something. All right, now, maximum and minimum values. First of all, we have definitions of absolute, also called global maximum minimum, and local, also called relative minimum maximum. Now, these are in your textbook, so you don't need to sit here and write it down word for word right now. You can also look at the recording and pause the video. The key thing I have highlighted. For the absolute, you are looking at the y value at that particular c x coordinate is the largest y value for all x in the domain. Now, if you're dealing with a function like sine x, there are a lot of c's that have that absolute maximum of 1. There are also a lot of c's that have the absolute minimum of -1. So know that your absolute maximums and minimums can occur at more than one x coordinate, but they only have one y value for each of them. And the big distinction between absolute and local, absolute is just the y value. It's just looking at what are the extremes in your range, what is the absolute highest, the absolute lowest of your range. So know that you can say f of c, but you cannot say c, comma, and write it as a point. If I use f of c, I am actually saying y value, but then you need to say the number that it is. For a local minimum maximum, it's about being on top for a short while or on the bottom for a short while. And I have the key bit highlighted that f of c needs to be greater than or equal to all the nearby f of x values when x is near c. And what does near mean? Near means trying to draw straight, an open interval containing c. So if this is x equals c right here, an open interval that contains c has some x coordinates to the left, and it has some x coordinates to the right, and it's looking at all the f of x values. They're pretty easy to spot, though. If I draw this, you can see, hey, look, it's a local maximum. Now, for the drawing that I just drew, if that's the whole graph, then there is a local maximum at x equals c, but there is also an absolute maximum there as well. So it is possible to be both. Now, here's an example of just some picture of a function. And when we talk about the absolute minimum, do you see that right here, it's the lowest that it is going to go? And can you see visually that up there is the highest it's going to go? So those are your absolute minimums and maximums. Absolute minimum is f of a, the actual y value itself. Your absolute maximum is f of d. If you look around, though, there are several local minimums and maximums. By the way, I will sometimes write local min as R min and local max as R max for relative minimum, relative maximum. It's a habit of mine because, you write something for a long time and it ends up being what you write without thinking. So if I'm going to list the local minimums, can you see where those are? So local minimum, C, comma, f of C, the point, and E, comma, f of E. Those are 2 points that are local or relative minimums. Do you see your local maximums? And I want to make sure to point out to you that this point, what color did I use for the other one? I used yellow. And f of d is both an absolute maximum and a local maximum. But when you write them, one is written as a point, the other is written as just the y value. Does it make sense why they would make the local ones be actual xy coordinates? Why is f of a? That is a very, very good question that was going to come up one way or another. X equals a doesn't have a left side. And in order to determine that something is a local minimum maximum, you have to be able to look a little to the left and a little to the right. So an endpoint actually can't be local extrema. And that's really one of those technical things that are hard to remember. If it turned up a bit, what? Be a local minimum and still be an absolute minimum. If it turned up a bit, it would. Oh, if it turned up a bit. So you mean that if you saw that and it connected? Yes. Yes, then it would be. It just won't be able to do that if it's an endpoint. Even if it looks like that's what it's about to do, an endpoint cannot check both sides, so it's never considered a local. Yeah. Okay. Then the extreme value theorem. There are 3 value theorems on the AP exam that you're expected to be familiar with, and this is the second of 3. We looked at intermediate value theorem already. You have to know the hypotheses of these theorems. They tend to show up in multiple choice, and this one especially will show up in a situation of like what must happen. Or so let me emphasize, you have to be continuous. and have specific endpoints of an interval. You have to be continuous on a closed interval, including those endpoints. If that is your situation, you are guaranteed that you will have an absolute maximum and you will have an absolute minimum. It doesn't say where they are, it just says they exist. And while that may seem obvious, you want to be aware of these theorems and what is necessary to be able to say that something for sure happens. And if you look at figure 5, there are 3 graphs to take a look at. All 3 of them are showing continuous over a closed interval. And take a look at each one and see that you do have an absolute maximum and an absolute minimum on each of these 3 graphs. So this is a highest point, lowest point. Highest point, lowest point. And then highest point occurring more than once, and a lowest point. There's only one answer to absolute maximum. Whatever that y value is there. I'll just say it's k, just to put something down. K is your absolute maximum. It occurs at 2 places, but it is the only absolute maximum. And it actually occurs at 2 places where it's also a relative maximum. And if you look at these 3 pictures, do you see that places where you have relative maximums and minimums are contenders for being an absolute? Do you also see that endpoints of an interval are contenders for being an absolute? That's very important in tonight's homework. All right, I am moving. Yeah. Scroll. Now, these are pictures meant to show you why you have to have continuity over a closed interval to absolutely guarantee that you will have an absolute maximum, absolute minimum. Figure 6 shows a discontinuity in the middle of the interval. And if I were to ask you what is f of 1 for this first graph, you would say probably 2 is f of 1. Is 2 the largest y value that you can see if you go a little to the left and a little to the right? It is not the largest value. And it's not the smallest value either. So let's take a look up here. Do you think there should be an absolute maximum there? If there is an absolute maximum there, then what number is it? 2.9999 If you say 2.9 repeating, what is 2.9 repeating equal to? It is actually equal to 3. I recall having this argument with my brother when I was a young girl. He's 7 years older than me, so of course he had to tell me, hey, guess what 0.9 repeating is? When I'm like, I don't know, maybe 8. And I just remember arguing with him. And I just kept saying, but there has to be some point 0.0000000000001 extra that isn't there. But at like 8 years old, I couldn't comprehend, or I was having difficulty comprehending the idea of infinity. Infinity is not an easy concept. To genuinely understand that 2.9 repeating is equal to 3 is not an easy feat. In fact, I've had students in calculus who wanted to go against me, I think more for fun, but just said, no, I refuse to believe it. But it's the idea that there are genuinely an infinite number of nines after that decimal point. And if I have an infinite number of nines after that decimal point, I can't just simply throw an extra 9 on and say that that's more. And that's why 2.9 repeating is equal to 3. There's some fun proofs with it, but I need to get on with the lesson. So this one does not have an absolute maximum. It does not have a real number that is in the range of the function that is the largest real number. And that's very uncomfortable for people. So again, I'm going to repeat, it has no maximum value. Now, figure 7. With that same idea, do you see that there is definitely no absolute minimum? Now, if f of 0 existed and it filled in that hole, it would be the absolute minimum. Yes. With x equals 2, we have a vertical asymptote. What is the absolute maximum if you have something heading up a vertical asymptote? And I'm looking in chat. Exactly, it does not exist. And it's the same situation of there is no real number that you can claim as the largest real number of that range. And that's why we always put round brackets on infinity when we write intervals. Like if I were trying to express the domain of figure 7, I would use a round circle for x equals 0 and, sorry, I just realized I'm mixing and matching my domain and range as I'm speaking. My domain is open interval 0 to 2. My range is open interval 1 to infinity. In order to have an absolute maximum or an absolute minimum, your range has to have square brackets. If it has round brackets, it doesn't happen. All right, moving on. If your derivative exists and you are located at a local minimum or maximum, do you have any option other than to have a slope of 0? If your derivative exists and you are sitting at a local maximum or a local minimum, is there any way you can get out of having a slope of 0? No. So that's Fermat's theorem. And you've probably heard of Fermat's last theorem, but this is not the last one. And just to make sure that you are clear about what can and can't happen, because the AP test is good at asking you questions like what is possible, what must happen. It is possible to have the derivative equal 0 and not be a relative maximum or a relative minimum. It is also possible to have a situation where your slope is not 0, but yet you have a relative minimum. So you want to be aware that a relative minimum and maximum, they can occur where the derivative is either equal to 0 or where it is undefined. That doesn't mean it will happen, but those are the places that are under scrutiny. If you have a derivative that is defined and it is not 0, you don't need to bother asking, is it a local minimum maximum? I remember one AP problem in a free response section, and I remember getting frustrated over it, going, I can't use the you'll find out later, but the first derivative test, second derivative test, none of them work. How am I supposed to determine if there's a relative minimum maximum at this point? And then when I looked at the answers, it was like, because the slope was like 1 or something like that. If you happen to know that the derivative at some x coordinate, let's just say x equals a, if you know the derivative is 1, and you are asked, does f have a local minimum or maximum at a? What should the answer be? Should be that it does not. It cannot. If the derivative is anything, any real number other than 0, I'm trying to highlight, and all I'm doing is scribbling. If I got negative pi, it wouldn't matter. If it's anything other than 0, f cannot, absolutely cannot have a local minimum or maximum. At x equals a. And the only reason you need to give is that. That is reason in itself. And if you think about it, if you have a slope that is either positive or negative, you're on the way up or on the way down. You are not at a local lowest or highest. And now we get an important vocabulary word. You must know this vocabulary word. Critical number. Critical numbers are values of x where the derivative is equal to 0, or the derivative does not exist. And we call them critical numbers because they're places that something important might be happening at. So they're critical. All right, now, if a local maximum or minimum occurs, it is located at a critical number. If you stop and think about that if-then statement, if you know that at C you have a local maximum or minimum, does that mean it must be a critical number of f? It absolutely does mean that. Now, just because you know C is a critical number, that does not make it a local maximum or minimum. But if you know something is a local maximum or minimum, you can definitely say it is a critical number. And these are the tiny things that the AP test will ask you in multiple choice that you've got to know well. And then it's time for an example. Woohoo! We're going to find the critical numbers of this function. And I personally would simplify this before I differentiated. So distributing, if I can speak this morning, x to the 8/5. All right. So if I'm going to find the critical numbers, I'm going to take the derivative. That's the first thing. So everybody, derive away. Derive. You have heard the phrase, don't drink and derive. Oh my gosh. Okay, well, you're deriving. When I was a little kid, I remember watching some public service announcement about not drinking and driving, and it showed like a bottle with ice cubes in it, and I was like, or like a glass, it had stuff in it. All I knew was that's liquid. It's like water. And I was like, oh my gosh. So when I drive, I can't drink water. Okay, good to know. The law doesn't say you can't differentiate equations while driving as long as it's in your head, but then you're distracted, so don't. All right, here we go. Taking the derivative, 12/5 x to the negative 2/5 minus 8/5 x to the 3/5. Now, your choices right now are you can make that negative exponent turn into a denominator and then go through a whole finding the common denominator. But I want to show you another way that a lot of people don't use, but you know, it actually, in my opinion, at least saves a good amount of time. Look at the exponents. You want to factor out the one that is numerically the smallest. So between negative 2/5 and positive 3/5, the smaller numerical number is negative 2/5. So I can factor out of that an x to the negative 2/5 power. And also a 4/5 while I'm at it. And when you're factoring, realize that you're actually dividing. So if I'm trying to figure out what's going to go here, I'm actually going to look at this 12/5 x to the negative 2/5 and divide it by 4/5 x to the negative 2/5. And hopefully you can see that that ends up being just 12 divided by 4, and we get 3. Minus. And then also realize that you are taking 8/5 x to the 3/5 power and dividing it by 4/5 x to the negative 2/5 power. And this is something you would do in your head, most likely. But if you actually did that in your head, can you see how that quickly turns super nice? So you use the exponent rule of subtraction. 3/5 minus negative 2/5 gives you the number 1. It's so beautiful. And then 8 divided by 4 gives you 2. So you are winding up getting just 2x. You didn't have to go through finding a common denominator and move that negative exponent to the denominator, because I've seen too many people accidentally say that that the function was equal to 0 at x equals 0. And it's about what your eye is seeing and making a quick judgment call. Anytime you have a negative exponent, it is best to write it in its positive format. So this is my derivative function. And now the critical numbers are anything that make it equal to 0 or undefined. Equal to 0 means what makes the numerator 0. And in this situation, it is undefined where the denominator is 0. So the critical numbers are x equals 3/2 and 0. Ready for another problem? Uh-oh, did we lose? No. I don't know why the Google Meet keeps rearranging itself on me. Never mind. Oh, yeah. We did have somebody drop and join or something. My number just went up. Okay. All right, next example. A lot of today's homework is going to be similar to example 8. You're going to be given a function that is continuous, and you're going to be given a closed interval domain. That means you will have an absolute minimum and an absolute maximum. Oh, from the last problem, the 3/2 comes from setting the numerator equal to 0 and then solving for x. Now, absolute minimum and maximum, they are either going to happen at a critical number or they are going to happen at an endpoint. But if you are not an x-coordinate who is an endpoint, and you are an x-coordinate who is not a critical number, is it even possible? Is it even remotely possible that you could be the largest or the smallest? No. Now, on the AP exam, if you just throw in a whole bunch of numbers into this function, you are not using calculus to solve the problem, and you will get no credit. You need to show that you understand the calculus. The calculus narrows down where to look. Once we determine where to look, all you need to do is make a table of values and find all the y values for the points that matter. The points that matter are going to be the beginning of the interval, the end of the interval, and any critical numbers between them. Know that I do enjoy putting on tests critical numbers or problems where there's a critical number outside the interval, and if you check it, you're going to get a wrong answer. You're only looking at critical numbers between the endpoints. So let's take that derivative. We need to find the critical numbers. Are 0 and 2 both x-coordinates inside that interval? Yes. When I write my table, I started off like this so that I don't accidentally start throwing in numbers who aren't in the domain. It helps me to not mess that up. It makes me focus on who I'm allowed to use. Okay. Then you have the joy of plugging these numbers into the function. Yay! And without a calculator. I like plugging 0 in. 0 gives me 1. I like you. And then we can sit here and go through the arithmetic. You guys can do it. I'm going to save myself breath and go over to what I did earlier today. I even had this ready because I didn't want to recalculate again. So we've got 1/8 when we plug in -1/2, -3 when we plug in 2, 17 when we plug in 4. So I'm going back over. Oh, why did it reset? Well, that's silly. Okay. Yeah. And now I'm going to need your help. This was 1/8, and what were the other two? -3 and 17 in that order. Thank you. This table, along with you finding the critical numbers, is full justification to, at this point, claim -3 is the smallest number, 17 is the largest number. So the absolute minimum. Now, it is okay if you say that the absolute minimum is equal to f of 2, which is equal to -3. Because when I say f of 2, that's referring to a y value. But if you know the actual number, you need to say it. I'm pointing this out because your textbook is going to write all of its answers this way. You do not have to say where it occurs unless they specifically ask you where does it occur. It is sufficient to just say absolute minimum is equal to -3 and absolute maximum is equal to 17. Especially if it occurs more than once, it's really uncomfortable to have to write that in an explanation. You just need to write that y value, boom, you've answered it. And are you dying for a calculator? Do you want some calculator time? The age of the textbook we're using is now going to become obvious when it says to use a graphing device to estimate. Although technically, if you write only so many digits after the decimal point, you are approximating. It's not exact, but sometimes you do get an exact answer with your calculator. Now, I'm going to talk to you a little bit about your calculator and things you need to play with and get to know. So, I've got a TI-84 to show you, and I need to see what I'm showing you. Okay. So I'm going to talk to you about the TI-84 and buttons that are on here. If you don't have a graphing calculator, the school can lend you one. And you might get an 83, but TI-83s have the same things as TI-84s. They just don't have as much memory and they're slower. And they don't have dun 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 LED. I love these. So pretty. Okay, so you are going to go to this y equals button. And then you can type in the function you want to type in. Now I want to point out to you, there is a mode button right here, MODE. If you click the mode button, you want, for the calculus exam, to have all the left side highlighted. You do not need to go into any other function mode. You can if you want, but whatever you do, don't leave radian mode. The AP Calculus exam is all radian mode only. So I don't know how well you can see from there, but radians should be highlighted. Where is it? There, now it's blinking. Make sure that you are in radian mode at all times on the calculus test. Now I'm going to go down, and right now function is blinking. And if you see what else is there, you can do parametric, you can do polar, you can do sequential graphing. And now I want you to take a look at a particular button. This one right here next to your alpha button. It says X, T, theta, N. Those refer to these function, and then parametric, polar, sequential. When you use this button as you're typing into this y equals place, it will automatically use a particular variable for the particular mode you are in. If you're in parametric mode and you push this button, you'll get a T. If you're in polar mode, you'll get a theta. If you're in sequential mode, you'll get an N. So you want to get used to just using this button as your variable button. So hopefully you guys have had a little bit of time to type in the lovely function. And then you can push graph, and let's see. Oh, my window's a little bit weird right now. But if your window is weird, you can, and I really don't like the grid on, actually. I need to tell it grid off, but I am not sure how to do that right now, so I'm not going to waste your time. If you want a standard viewing window, -10 to +10 for X and Y, go zoom. Do you see the middle button right there, zoom? Go zoom standard. So zoom, and then find standard down that menu. It should be number 6. You can literally push 6, and it will just change it to a -10 to +10 window for both X and Y. And notice it is rectangular. Now, there's a certain area that you need to get very familiar with. Are you ready? This is super important. Okay, there's a certain menu, very, very valuable. If you push the second key, push second, and then push trace to get calc for calculate, not calculus. Everything in this menu is useful to you. For value, if you push enter on that, you can then type in whatever X coordinate you want, push enter, and it will move your cursor to that point and tell you the exact XY coordinate. For 0, the 0 menu, if you do that, it's going to ask you for a left and a right bound. And depending on the age of your calculator, it'll either say left or lower, and then right or upper bound. You have to make sure you have something that's negative and something that's positive. Otherwise, it'll tell you error. But if you have a continuous function and you've got a negative that you put in and a positive that you put in, it will tell you the x-intercept. That's very, very valuable for solving equations. So I recommend play with that, see what it does, see how useful it is. I want to repeat, you can solve equations. So you can take a left side of an equation minus the right side, put that in your calculator, find the 0, that is the solution. And you can see how many solutions there are. Another way to do it is using the intersect. Does everyone see? Oh, it's starting to. Intersect is number 5 down this menu. With intersect, it allows you to take, say, a left side of an equation and graph it, and a right side of an equation and graph it. You can find the intersection of those graphs. The x-coordinate of every intersection point is a solution to the equation of left side equaling right side. So you need to be able to solve equations with your graphing calculator. That is one of the things that you have to be able to do on the AP exam, because you're not going to find it without a calculator in the calculator section. Now, some other things that they do. Minimum, maximum. It will find it for you. You just tell it the domain. If you push enter on one of those two, you will see that it asks you Like if I want to find a minimum, it's asking me, did I push the right button? Hold on. I think I pushed the wrong button. So I'm going to go with minimum, pushing the number 3. It's asking me for a left bound. So I am to the left. I pushed enter. Then it asks me for a right bound. I use my right arrow and I go over until I am to the right of that low point. And then I push enter. And it gives, and then it asks, it says guess, and you push enter again. And then it tells you that exact minimum, X and Y coordinate. But if you're on the AP test and this is a free response problem, you using this minimum maximum capability of your calculator is only to check your answer. You are expected to show the calculus work behind finding minimums and maximums because it is a key thing that calculus can do for you. Even though our technology will find it faster than we can ourselves, the idea of applying calculus to a real world problem. There are a lot of real world problems where you need to maximize something or minimize. Like, hey, if you're in business, you might want to maximize your profits. Don't want to minimize them. And so if you're able to get a function model for your profits or who knows what, you can find maximums and minimums to help you estimate when something's going to happen. There are whole fields of applied math that are out there. But when it's applied, it's more an issue of estimation. You have to deal with the fact that math is ideal, but, you know, biology and stuff do not have to follow what it is. Or, you know, you can't tell a mother you can't give birth yet. I'm waiting for a particular time for our population to grow. Anyway, I need to keep going because we've got 5 minutes left. And if I need to, I'll keep recording and finish going over what I'm doing. Okay, so you need to use calculus. So you are going to take the derivative of f of x. And you are going to find any critical numbers in that interval. With a cosine function, it will never have a discontinuity. So we are looking at what are the angle numbers that make cosine equal to 1/2. So cosine equal to 1/2 is the first x coordinate to the right of the y-axis. And that is where our angles pi over 3 and 5 pi over 3 land. Then make an xy table. In your homework, I expect you to solve this without a calculator up to a point. And I'll explain. If I plug 0 in, I know I get 0 out. And I'm plugging this into this f of x right here. If I plug 2 pi in, the sine of 2 pi is 0, so I can quickly just say 2 pi because it's x minus 2 times the sine. For the other two, you need to get to the point where you have used the unit circle to find the number. So when x is pi over 3, f of x is pi over 3 minus 2 times the sine of pi over 3. And With pi over 3, the sign is, if I had drawn a better circle, it is the highest x-coordinate, I'm sorry, the highest y-coordinate above the x-axis, so it is root 3 over 2. And then with 5 pi over 3, its sign value is negative root 3 over 2. At this point, pull a calculator out. You need to practice using your unit circle, but I do not expect you to go through painful estimation to try and figure out who's largest and smallest. So once you get here, you can, you can use your calculator to get these numbers. And then you are able to say the absolute minimum and maximum. And it looks like I did not finish writing my answer, or I accidentally erased it. I think I probably accidentally erased it. So absolute maximum happened at 5 pi over 3. But what's important is the actual y value. Okay. Now, you're supposed to be moving on to lunch, but if you want to stay, you can, because you want to hear this next bit. So if you leave, make sure you watch the video when this problem pops up. And I'm going to keep going. Technically, it's only 10:44 still. But anyway. All right, here we go. You are supposed to figure out at each of these x coordinates, are you dealing with a relative minimum or relative maximum or an absolute minimum or an absolute maximum or none? So let's start with A. A, oh, wait a minute. No, never mind. Sorry. At x equals A, it is an endpoint. That automatically means it will not be a local. Endpoints are not allowed to be considered for local minimum maximum. Now, visually, does it look like it is the lowest y value? And it is meant to look like the lowest y value. So you can say that at x equals A, this function has an absolute minimum. And sometimes we say absolute, sometimes we say global, sometimes they say just minimum. If the word absolute or local do not show up, assume absolute if they don't put a word with it. All right, let's move on to B. Where is f of B? The actual point is right here. F of B is this y value. You have to know these definitions to be able to answer these questions correctly. The definition of local minimum maximum says that you need to look at an open interval containing B. Is that value, f of B, greater or equal to all f of x values for a small interval of x containing B? Yes. That means that you do have an absolute maximum there. And you can have an absolute maximum occur at a not absolute, relative. You can have a relative or an absolute occur at a discontinuity. So at x equals b, f of x has a relative, and I'm just going to put r, relative maximum or local. Moving on to c. Look at where f of c actually is. Where is the filled in point? If I look a little to the left and right, and I look at those f of x values, can you see that it is not a relative extrema? And it's all about an issue of this is the point that's filled in, not this one. As to why in this case, at x equals c, you do not have a relative extrema. And it's not an absolute either. None of them. Moving on to D. Hopefully you can see that D is definitely a relative minimum. And hopefully you can also see that it's not the lowest point. So it's a relative, but it's not an absolute. Then let's move on to x equals r. We do have the derivative does not exist at r, but we do have a relative maximum. And in fact, is at the highest point as well. So at x equals r, it is a relative maximum or local maximum, and it is the absolute maximum. And lastly, S. S is an endpoint. A lot of people will accidentally say that it's a relative minimum because it looks like a low point in the middle of a parabola. But if you don't know what goes on the right side, this could have been a negative x cubed graph. Just because the slope is 0 at an endpoint does not make it a relative minimum maximum. You have to be able to look at both sides to determine local minimum maximum. It is also not the lowest point, so basically just none. It is not a relative minimum maximum. It's not an absolute minimum maximum. And it is now time to go. And I just finished. Woo! I will see you tomorrow. Enjoy your homework. Yep, you too.